Hello, this is Liz here from Maths for Granted, and today we are going to be doing some A-level maths, and the topic is proofs. Not many students' favourite topic, and I will break it down into AS level, probably stuff that you will see in year 12, so that will be today's video. And then I'll do another video of the types of proofs you will meet in year 13, in particular proof by contradiction, which I will do that as a separate video. So the proofs that you will probably meet in year 12 are basically proof by deduction, which we'll have a look at first. You'll also meet proof by exhaustion, which is not too difficult. And sometimes you may even be asked to show that something isn't true, so to disprove something, and in fact that's probably the easiest thing of all, so we'll finish on that one. Okay, so let's have a look at proof by deduction first. So a proof must show all assumptions you are using have a clear sequential list of steps that logically follow and must cover all possible cases. You should usually make a concluding statement. Often you restate the original conjecture that you have proven. Okay, so no missing any algebraic stages. Go through each line carefully, each stage of work carefully. Okay, so let's have a look at some. So proof by deduction, this is the simplest type where you start from a particular fact and then you reach the desired conclusion via deductive steps. So involving lots of different algebra, often involving completing the square, you will see later. Okay, prove that the product of two odd numbers is odd. So what you need to remember from GCSE is how you demonstrate that we have an odd number and then a different odd number. So I don't know if you can remember. We often start it off by something like this. Let P and Q be integers. So P and Q can be odds or evens. And then if you double any odd or even number, it will obviously make it even, won't it? But then if you add 1, 2P add 1 then is definitely odd. And then if we have 2Q add 1, that is also an odd number. Okay, so that's the sort of first defining our odd numbers. And then we've got to prove that when we multiply them together, you will definitely still get an odd number. So we've basically just got to perform expansion of two brackets here. So 2P times 2Q is 4PQ. 2P times 1 is 2P, 1 times 2Q is 2Q, and then of course 1 times 1 is 1. And then hopefully you can spot, if you want to prove something is odd, you really need it in this form where you've got everything else having a factor of 2, and then if you can have an add 1 separately, then it must be odd. So I don't know if you can see in these first three terms you can take out a factor of 2. So then all of this, 2 times anything here, all of that will then definitely be an even number. But then, of course, we've got a plus 1 on the end. So this is 1 more than a multiple of 2 and is therefore odd. And I suppose you should perhaps say at the end, therefore the product of two odd numbers is odd. So that's that one done. You may just be asked to show an identity is true, and these are quite nice proofs if you're good with simplifying expressions and good with your algebra. So an identity is an equation that's true for all values of a particular variable. So if you've got x squared equals 4, this is just an equation because it's only true when x is obviously positive or negative 2. An identity, we use 3 horizontal lines and say something like this, x bracket x take 1 close bracket is always going to be identical to x squared take away x, and that's true for all values, isn't it? So a common mistake students do is they sort of try to go about solving these. So we don't solve an identity, The general method is you start with the left hand side and you perform various steps of algebra on it until it turns into the right hand side. So you do not generally use this side. Some students often sort of, go halfway with the left hand side and then go halfway with the right hand side, which is okay. So let's have a look at trying to prove then that these three brackets is identical to this cubic expression. Okay, remember you're not solving it as an equation. So look what we do. I've just started with the left hand side only. So the first stage I'd be showing the examiner I'm multiplying out two of the brackets, so they've used the second two. And then I expand 3x with all of this and 2 lots with all of this, and that's all of my line of work. And then I simply neaten it up. That should say 3x cubed. I've just spotted there, shouldn't it? And then you've done it. You have turned your left hand side into your right hand side. And then remember, we restate the original. Therefore, those three brackets is identical to this cubic expression. So identities are often quite nice to do. Remember, do not solve them like an equation. Okay, let's have a look at some more. Proof by deduction requires you to start from known facts and end up at the conclusion. It is not acceptable to start with the conclusion and verify it works because you are assuming the thing you are trying to prove. So here's a typical sort of question where some students sort of tackle it the wrong way round. Prove that if 3 consecutive integers are the sides of a right-angled triangle, then the numbers have to be 3, 4 and 5. Okay, so this would be an incorrect proof. Let the lengths be 3, 4 and 5. So look, we're assuming the thing we're trying to prove. So then we go about using Pythagoras, which is fine. This satisfies Pythagoras' theorem and the numbers are consecutive. So you've basically proved there, haven't you, that 3, 4, 5 would be the sides of a right-angled triangle. But you haven't proved, of course, that they're the only 3 consecutive numbers that will work. You haven't proved that there could be others. You've just proved that that makes a right-angled triangle. So what we have to do is we start the opposite way round. We start with explaining that we've got 3 consecutive integers. So hopefully you've seen that sort of thing at GCSE, 3 consecutive integers. You could have x add 1, x add 2. So we're allowed to assume that that's what we've got there, x add 1, x add 2. And then we perform Pythagoras, so x squared add the middle side all squared should be equaling the hypotenuse squared. And then, of course, we neaten it all up. So neaten all of that up. And then hopefully you end up with a basic quadratic that we can factorise. And x can only be 2 answers, -1 or 3. But we are talking about sides of a triangle. So, of course, x can't be negative. So the only solution that we actually get then is x has to equal 3. Which then, of course, means if x is 3, x add 1 is 4, and x add 2 is 5. So therefore, you've then actually proved what we should have done. Okay, now this is a really common one. Prove that x squared add 4x add 5 is positive for all values of x. Okay, so we've got to somehow prove that this quadratic, imagine you've got to say y equals x squared add 4x add 5. So it's sort of saying the y coordinates always have to be positive. Anything like that, we usually start with completing the square. So hopefully you are fine with completing the square. You've met that already. So half the x coefficient, imagine you're then taking away the square of that, which would be -4. Add the 5 would be +1. Now this is the important thing you must then explain. You need to understand that if you square anything, it's got to be at least 0. So, you could have a negative number here, couldn't you? Something like -10. -10 add 2 is -8. But when you square it, it will become positive. So the lowest this can be, hopefully you've met this idea before, the lowest that expression can be is when x is minus 2, and then you'd get 0 squared is 0. That's the lowest it can be. Well, if the lowest this can be is 0, and then we add 1, that means that whole expression then has to be at least 1, which is bigger than 0, which must mean it is positive. That whole thing there then has to be positive. And let me try and show you. I don't know if this will work, but if I was sort of sketching that quadratic, apologies here by, oh dear, that's meant to be my axis there. Okay, so I know the minimum value, hopefully you've met this idea before, is minus 2, 1, something like that. So that there is minus 2, 1. So I can see visually I'm never going to get any values below 1, in fact. So we've proved that this quadratic expression will always be positive. Okay, let's have a look at another one. Prove that the sum of the squares of 2 consecutive odd numbers is 2 more than a multiple of 8. Okay, now they've got to be consecutive odd numbers, so a little bit different to that one we did earlier. So let's have a look how we do this. I don't know if I've got to get rid of, let me have a look. I think I've just got to get my arrow back here. Okay, so if I want consecutive odd numbers, we've seen before we need to have an even number. Look, an even number take away 1, and the same even number adding 1 will produce consecutive odd numbers. Okay, and then the sum of the squares, so I'm going to square this one, 4n squared, take 4n, add 1, and then square this one, 4n squared, add 4n, add 1. And I want the sum of those, so I'm going to add these together. Well, that will make 8n squared. These 4n's will cancel, so I've got 8n squared, add 2. Well, this here is clearly a multiple of 8. Whatever n is here, that will always be a multiple of 8, won't it? Because I'm timesing by 8. And so therefore, if I add 2, it's always going to be 2 more than a multiple of 8. Okay. So that's the end of proof by deduction. I would say it is really important to do lots and lots and lots of different examples, different sort of identities, lots of different proofs, practicing completing the square. Let's have a look at this one. Proof by exhaustion. Okay, now these are often easier to do. This means breaking down the statement into all the possible smaller cases where we prove each individual case. Let's have a look at this one. Prove that n squared add n will always be even for all integers n. So we're going to prove that it's true for odd numbers, and then we're going to prove that it's true for even numbers. But often you get much easier ones than this. You'll get some sort of statement and they'll just say prove that this is true for values of n between 3 and 10, say, and you literally have to check the values 3, 4, 5, 6, 7, 8, 9, 10, and that is proof by exhaustion, where you've proved it for each particular case. Okay, so let's have a look what happens if n is even, because n, if it's an integer, it's either even or odd. So let's see what happens when it's even. Okay, n squared would be even times even, and then we add an even. Well, even times an even we know is always even. Even add an even we know is always even. So I've proved it for even numbers. Let's check it's true for odd numbers. So now n is odd. So I'm doing n squared, which is odd times odd, add n, which is odd. So odd times odd is always odd, isn't it? But an odd add an odd is always even. So we've actually proved it for all cases, every single even number, every single odd number. Therefore, it is true for all integers. But like I said, you'll often get much easier ones than that, but make sure you set your working out clearly and you show each individual case. Now, to disprove something, or we need to disprove an argument, is one example where it doesn't work, and this is called a counterexample. So, while to prove a statement is true, we need to prove every possible case, basically an infinite number of cases. To disprove something, we only need one example to disprove a statement. This is called a counterexample. So sometimes it might involve trial and error, and you keep trying different values until you find one that shows that it doesn't work, that you've disproved it. Let's have a look at this one. Disprove the statement n squared take away n, add 41 is going to be prime for all integers n. Now you might want to sort of do it by trial and error. I had a look at this earlier, and you could do n equals 1, n equals 2, n equals 3. But in fact the logical thing to do is have a look at this number. See what happens when n equals 41. So if you've got n as 41, look, you'll get 41 squared, take 41, add 41, which means they'll cancel, and then you're left with 41 squared. Well, 41 squared, whatever that is, will certainly not be prime because, of course, 41 is a factor of 41 squared. I've got to tell you what that is, haven't I? It's 1,681, of course. And we know 41 is a factor, which means 41 squared cannot be prime, so thus the statement is not true. So disproof by counterexample is really easy. You only need to show it doesn't work just for one particular case. Okay, that's the end really of proofs that you'd meet in year 12. I will do another video of a method called proof by contradiction. There is another lovely type of proof called proof by induction, but that would be sort of for further maths A-level students. Okay, thanks to Dr. Frost for that PowerPoint, and thanks for listening and watching, and I will see you again soon. Bye.